Another reduction reaction that's featured in this chapter that is built on a review reaction is the reduction of carbonyls all the way down to a CH2 group. This is actually very useful. For example, if we do an aldol reaction or another addition reaction like a conjugate addition reaction, we end up with a carbonyl in our product and we don't want a carbonyl in our product. To get rid of it, we will need to reduce it off. Now, we've already seen one way to do this through a Wolff-Kieschner reduction in a previous chapter, but in this chapter we're giving two other options. And the reason we might want to use different options to do this is because sometimes our carbonyl is in the presence of other functional groups that might also react. So for example, there's a second way to do this. Using zinc mercury amalgam, we want to use a different set of reagents. If the same compound has nothing that will react with acid, then zinc mercury amalgam and HCl might be an appropriate choice. A third set of reagents for this reaction is Raney-nickel reduction. This reaction goes through first forming a thioacetal. So you start with your carbonyl, you form an acetal, much like you would if there was oxygen on both ends, and then the sulfur-oxygen bonds are cleaved and replaced with CH bonds with the help of a hydrogenating agent using hydrogen gas and a special catalyst developed by a chemist named Raney-nickel. These conditions are different yet again from the previous two. They don't require a super strong acid to make the thioacetal, and they require no acid at all to do the reduction. So as long as you don't have groups that will react with hydrogen and Raney-nickel in your compound or with thioacetal and trace acid, then you can use the Raney-nickel reduction. So these are expanding our toolkit of how we would reduce a C double bond O, a ketone or aldehyde, to a CH2 group. We can do it the way we saw in the previous chapter, which if you want to look at this mechanism, it is in the video for chapter 18. Or we can do it with a zinc mercury amalgam and acid, or we can do it by creating a thioacetal followed by Raney-nickel reduction. Our final topic for this chapter is protecting groups. And protecting groups are things that we put onto molecules so that they won't react when we're reacting some other part of the molecule. For example, if I had a molecule with both an alcohol and a carbonyl in it, and I wanted to react exclusively at the carbonyl here without interfering with my OH, then I would have to protect my OH, make it into an unreactive group through a chemical reaction. The most common protecting groups for alcohols are ethers, and there is a list of ethers you can make, all with the help of a little bit of acid and an appropriate substitute for an R+. These protecting group reactions will allow us to put the protecting group on, and each of them is a reversible reaction, so that if we add excess water later, we can remove that protecting group and get back our original alcohol functionality. Now, if we didn't do any chemistry to the aldehyde while we were protected, this would be a pretty useless sequence. We start with something, we put a protecting group on, we take a protecting group off, we lose some material at each level, and we end up where we started. So of course we'd have to do some sort of chemistry on the intermediate, specifically focusing on the carbonyl in between to make this a useful sequence. Another scenario we can imagine is that we might want to do some chemistry over here on the alcohol group, but not involve the carbonyl. For example, if we wanted to oxidize this alcohol group, but not this carbonyl that we already have, we would need to protect this carbonyl since aldehydes are readily oxidized. So to do that, we need a protecting group for our aldehyde. And the most common protecting groups for aldehydes and ketones are ones we saw in chapter 18, acetals. Acetals are created in the presence of dilute mineral acid that shouldn't mess with a primary alcohol. And the most common of these acetals that's used as protecting groups is using ethylene glycol or 1,2-dihydroxyethane as your alcohol source to make the acetal. And of course, acetal formation is reversible. In the presence of dilute acid in water, it will be removed to get back our original compound. Again, this would be a somewhat useless reaction to protect and deprotect unless we also did some chemistry on the end in the meantime. The protecting group reactions to make primarily ethers for alcohols or to make acetals and other protecting groups for carbonyls are summarized in the CARDI table 19.2.